Hey Wheaton North, Mr. Yergler here. In this video I'm going to talk about two different things. I'm going to talk about atoms and ions, as well as the relationship between the distance between those particles. So let's first start with ions and atoms, kind of as a quick review. You should be familiar with ions by now, but I do want to kind of go over it a second time. This is a simulation that I found online. There's a couple different ones out there. You can just kind of Google build an atom if you want to try and find them. It's very similar to the PhET simulation that you should have already used. This one I like because it has more than just the two outside rings. Alright, so let's start with, I'm going to type in a capital F here for fluorine, and let's start with fluorine. It'll build me a fluorine atom. Now fluorine has 7 valence electrons. It has 7 electrons on its valence shell. And we know that atoms prefer to have 8 in their outside shell, in the valence shell. That's what makes the atom most stable. And atoms always typically do whatever makes them the most stable. Okay. Now, fluorine also has 9 protons in the center, so 9 positive particles in the center. The protons are positive, the neutrons are neutral. They have no charge. The reason that fluorine has 9 protons is because it's fluorine. Anything that has 9 protons is going to be fluorine, and fluorine is always going to have 9 protons. The number of protons is what determines the identity of the element itself. So if I were to add one more proton, it would actually change the identity of the element itself to neon. That actually never happens in nature, except maybe on the sun or in very, very hot and large stars, because it requires so much energy. So what is much more likely to happen, in order to change the charge, that is the changing the numbers of electrons, because these electrons are flying around the outside of the atom, outside the nucleus, and so they're kind of on the very edge of the atom, and they're very easy to remove or add when reactions take place. So notice now that we have neutral atom. There are 9 positives and there are 9 negatives, right? So they balance each other out. If we were to add one more electron, and fluorine actually does do this quite often, it makes it a lot more stable, because now all of a sudden the valence shell is full. There's 8 valence electrons, which is what makes the atom stable. And so fluorine will actually do this relatively frequently. It will often gain this 1 electron, giving it a -1 charge. And that's why fluorine, all the halogens, fluorine, chlorine, iodine, bromine is another one, they all form these -1 charges because they have that 1 slot open on their valence shell, right? And so when an electron fills it, it makes it so that there are 1 more negative electrons than there are positive protons. Okay, and that's what forms an ion. So forming an ion is really simple. It often confuses people because they don't really understand what's happening to the electrons, or they don't understand why the charges are changing. But a fluorine atom, a neutral atom, let's go back to neutral. A neutral atom becomes an ion simply by changing its charge. Now this could happen, I'm showing a negative ion. It could also happen theoretically by forming a positive charge, right? So now we have a positive ion. Fluorine never forms a positive ion. It always forms a negative ion because it just needs that one more electron to fill the outside shell. So it's always going to grab 1 electron rather than losing 2 electrons, for example. Now, that is how ions form, and that's all ions really are. They're just charged particles. So anytime you have a different number of protons than the number of electrons, you're going to have a charged particle, and therefore you're also going to have an ion. Okay. Now this brings me to my second point, which is kind of what the Coulombic attractions worksheet, that worksheet 7, is trying to get you to understand, is that not only do the numbers matter in terms of charge, but in terms of forces, the distance also matters. And so if we were to add 1 more electron, let's say I add 1 right here, now all of a sudden the valence shell is no longer the second shell. Now the outside shell is the third shell. And that third shell is a lot further away from the nucleus than the second shell, right? And just like how magnets get weaker and weaker in attracting each other, the further you further away they are separated, right? You bring magnets closer together, and they're going to attract each other a lot more strongly. Same thing happens here. These negatives and positives attract each other, but not as much if they're far away from each other, right? If I were to bring this negative in here, it's really strongly attracted. Take it way out here, it's very weakly attracted, because distance makes a big difference. What also makes a big difference is the number of positives you have in here. So let's add a bunch of protons to make this very positive. So we're increasing the strength of the positive nucleus. Okay, and I'm going to balance it out with 3 more electrons here. So hold on just 1 second. This takes me a little bit. Now all of a sudden we have a neutral atom, sulfur, because we have 16 total protons in there. That's what makes it sulfur. Now this is going to be an actually smaller atom. The model doesn't show this. This is a kind of negative aspect to this model, this particular simulation, is it doesn't show the changing size of the atom. But as we make this more and more positive, we're making that force, that charge, much stronger. And so as we add these electrons, because they're going in on the same distance in the same shell, they're actually going to be pulled closer together, making the atom itself slightly smaller as we add more and more positives, right? As you make this more and more positive, it's going to draw in those negatives closer and closer because the force is going to be stronger. If we were to all of a sudden add electrons to the outside shell, to the next shell, so we fill that shell and then we add one more, now all of a sudden they're much further away from each other, the valence shell is, and so now all of a sudden it's going to be much weaker force because we've changed the distance significantly by going on to the next valence shell. Okay, so this is what that Coulombic attractions worksheet is getting at. The distance and the number of particles in the center, the strength of the charge and the distance of the charge make a big difference in how the size of the atom changes. Okay, there's another video called shielding that kind of is a continuation of this video, so make sure you check that out. And this is Mr. Yergler signing off.